Hello, Luca.
Hello, Thomas. It's been 2 weeks.
Yeah,
We skipped the last one because we wanted to crack some aspects of running Hugging Face in inference, um, and we did. Like we by using CUDA graphs, which are this magic thing that intercepts all the kernels, put them together, well, not together as in one kernel, but helps with the scheduling. Um, we were actually faster than the alternatives. But the problem is that without CUDA graphs, we didn't see, like, we saw some extra latency. Story is that we're still looking for the culprits, right, Thomas?
right. Yeah, and there's a whole can of worms where I wanted to optimize a bit, and then there are like a bit of refactoring going on that turns out to be very detailed. But yeah, so
Nice.
this is when you report live how the sausage is made, I guess.
Absolutely. Yeah,
Yeah,
yeah, exactly. So, long story short, if you tuned in because you wanted to see the non-CUDA graph latency being great, we don't have that yet. But since
yeah,
we can now run Hugging Face Llama, we wondered that like we have a story for inference and it will get better independently on CUDA graphs eventually, shortly enough. But there's another side of the story which is training. So is Thunder capable of running Hugging Face Llama in training as well? So training means forward and backward. Now the question is, to you, Thomas, can we do
yeah.
that?
I mean, in order to do that well, and a few weeks ago you announced your new glasses, yeah, and in
Oh
order to
wow!
step up the game, I got a pair of
Woohoo!
like glasses, and now I hope I have the same great insight as you have. I think.
Absolutely, yeah. If anything, I should put your model on, not the other way around. But if you want to come into the magic land of like not really having a clue, welcome.
Well,
All
we'll
right.
see about that. And
Yeah,
you can talk to us in the comments and tell us whether the glasses helped or not.
yeah. If it makes you dizzy, we'll fix it in the next episode. All right.
Right.
Um,
Okay.
so I would say that we fire up a studio, we explore the forward backward thing on Llama a little bit, and then maybe we scribble something if something needs to be clarified. But I think there's a number of things in the compiler world that differentiates inference from training. And yes, it's the backward, but there's some more consideration about that. Like it comes with a lot of when you run a model and you don't go out of memory when you run a model in training and you don't go out of memory, there are certain things that make you not go out of memory that you might not be aware of. And today or the next time, we'll try to elucidate what happens and how the sausage is made during training. All right. So
Yeah.
new notebook, clean notebook, incredible.
Clean notebook is something where I didn't write anything stupid yet. No stupid coding mistakes anywhere,
Absolutely.
except for the preloaded libraries. Of course, the great thing about the studios, the advertisement block is here. The great thing about the studios is that they persist my environment. So I
Yep.
have the latest Thunder version I deployed. And of course, I have also installed transformers. So let's import from transformers models llama.
And while you do that, a lot of people use transformer models. Um, we love our minimal libGPT. So it's not that we're abandoning libGPT. libGPT is great. 400 lines, you have all the model there. You don't have to go around looking for where code is, where things happen. But to us, and Transformers is an amazing library. It contains so much stuff, but it's also very complex. Like the amount of complexity you have in there, complexity not just about how many models are there or how they are organized and split up, but also the constructs that are used to allow this flexibility, a lot of use for dictionaries, classes inside classes, and so on. So to us compiler people, it's quite a moment where you finally get to run through transformers, because you will find every single Python construct out there in there. And so if you can then run it, then it means that you understand a lot of Python, a lot of PyTorch, a lot of stuff. And so that's why we're so focused on transformers right now, also because it's a natural entry point for people wanting to try out the compiler for our coming first public release, in early 2025. Well, public, it's already public, but let's say the moment where we call people in and say, like, now, use it, you get good performance.
Right. And so similar to last time, we're using Llama 3.2 1 billion model. And we instantiate that on the device. And so, as Luca said, well, Transformers is a great library. And while you have this effect that when you see user code for any given thing in Python, it will be like very friendly and very understandable. But if you get to these large libraries, whether it's PyTorch or Transformers here, they usually have like an unholy amount of magic going on behind the scenes. Like when you run things, there will be regular expressions being run and all that sort of stuff. And so, at some point, like Transformers uses introspection to find out what kind of parameters functions take, and so that's all like very obscure code that doesn't have, well, obscure in the sense that it doesn't have much to do with our primary goal, which is to run like deep learning models on the GPU fast, right?
Yeah.
Okay, so what I'm doing here is I'm setting up, and it's cute,
Cute,
nice, probably, right?
Cute, why not?
Very cute. Okay, so I will just use very lame input IDs and labels. Usually you would get them from the tokenizer. The thing is, when you have this training setup, you typically have inputs and labels, targets. And so, okay, we can check if we can run the model with these inputs.
There's no thunder so far.
No thunder so far. But obviously it helps if you know whether the model runs. And also, I'm hiding all this funny business, or some of the funny business that gets run during the lazy setup, if you want, which is cheating a bit. But yeah, you can also use the recipes that we introduced a couple of episodes ago in order to make this very easy.
Oh, yeah, by the way, yeah, the recipes, of course, everything we're doing here will result in a recipe as soon as possible. So we'll have recipes for Hugging Face models very soon.
Yeah. Okay. So when you run the model, you want to run JM with the arguments, and then you will see that yeah, it runs a bit, and I run the full llama here that has 16 layers or something, 16 blocks. And then we can see the result. Typically, the Hugging Face models, they return bespoke classes for the results. And so we can look at what we get there in order to see what we need for the training. And if you're in the deep learning training mindset, if you want, you know that you have the forward and then you have the backward, and then you imagine that there's a training step too. And so here we're running the forward, and yeah.
Yeah, one of the interesting thing is that if we have like classes or dictionaries as inputs or outputs of our model, what Thunder does, right, will unpack those things into kind of pure um, inputs, and then to in the prologue to then pass them on a very like super functional
Right.
computation trace, and then it will return. Is it if it has to return an object in the output, it will do it in the epilogue trace, so that when you transform your computation, you're presented with something that doesn't have that complexity. I think this is very worth stressing out. Like we do everything we can to present anything right in a transformation, something that is uniform. It's canonical. I think it's a very canonical way of expressing computations
Right.
in deep learning.
So if you look here, you have this causal LLM output with past. Obviously, we could try to convince Hugging Face to return less of this, but so the important bit is the loss. And we see here, well, it has a value, it's a scalar tensor, and then it has a gradient fn, which you know from PyTorch, of course, and if not, you can always check out the book. Obviously, still a great book, and the way I got to know Lucas, so that's
Oh
cool.
yeah,
So
yeah,
what we do then is we compute the backward for the loss, and this will give us the gradients, and ultimately, like show allows us to take a step to reduce the loss. So, but now we have like these two bits, and if you remember correctly, or if you remember the details, we can see like what computations Thunder did here. So
mm-hmm.
can go Thunder last traces and pass in the module, and we want
Yep.
say the last one.
Yeah, an interesting thing here is that Thunder, as we explained, and maybe we'll get back to it, Thunder includes an autograd or auto differentiation pass
Yeah,
under the form of a transform. But here we are calling backward, and we saw gradient function, which is what autograd from PyTorch does. So what happens here is that basically the entry point is Torch's autograd, but then we then compute the whole backward thing. So it feels like PyTorch, but in the end, we're not using PyTorch's autograd in this particular case.
right. And if you see this here, you see that this has the last trace, the one that's
Mm-hmm.
executed. We see that it has all the weights as
Mm-hmm.
arguments, quite a few, and then it has the computation as the straight line program. You can see that it's calling linears, it's calling NV fusions, and it's calling torch compile things. So it dispatches to various optimized computations. And at the very end, and for this large program, there's a very that is quite a long thing. You see that it returns quite a structure, and
Yeah.
this has to do, well, it needs to return the output, but the functional form will also return things that are saved for autograd. If I can find it, here it has the flat arguments, which are needed for autograd as well for like technical reasons. And somewhere here there should be a thing that says save for backward. Let me try to.
Mm-hmm.
No. No saving of things. Okay. So apparently, like something is
Let me
going
check
on.
something. Yep. Let me check.
We would need to figure out like what's maybe it's just another argument here, but it's this part here, the tuple at the end that gets saved for backward, and we see there's quite a bit, and we'll go into like what this actually does in a bit. But if you want to see how Thunder has its own autograph or auto differentiation engine, you can start with the initial trace, and as last trace is 0 is the program as seen by Thunder. And there you can see that it just runs the thing, and then it returns just the output and nothing else. So this will be the
Yep.
output, and you can see that it kind of remembers the passkey values, which we wouldn't need, strictly speaking. But then if we like go further, we can see that at some point remove context manager prims, which takes care of autocast and stuff like that. And then there's that code elimination, and eventually we have constructed by augmented forward pass, and that is the bit that constructs the forward and the backward, and the forward will be the augmented forward, and we'll discuss in a minute what that is. And then we have the last backward traces to match. And this is the thing that then grabs all these saved for backward items and unpicks them here again. And so this is then the backward that is run. And as you can see, it's a Thunder trace as well. And this is also constructed during this forward-backward construction. And
Yeah. So basically, the trace is acquired just in forward, and then we require to turn that into an augmented forward by basically taking each op and calling the augmented forward for the op instead of the original op. And the original op would break down operators into primitives. The augmented forward will do something else, and maybe we can quickly take a look at one rule to remember, because we already touched upon this, but it's interesting because, and we'll show you in a second, but if you need to compute, so what is the backward? The backward is ends up in computing the partial derivative of the loss, which is what you call loss dot backward on, with respect to all the tensors that have required ground true, which are the parameters of the model. And to get to there, there's a lot of like chain rule of derivatives thing, which requires you to basically use all the intermediate results that you generated while getting there to the loss and reuse them. And so that's what you need to save for backward. Save for backward means I compute an activation. That activation will enter my analytical computational derivatives at all stages. And so I need to have it there, to have it saved somewhere so that I can reuse it. And what is it that is not great about this?
right,
Necessarily. I mean, it's great if you have a lot of memory. If you don't have a lot of memory, you end up saving all the intermediates that you computed along a very long model, which is a large transformer. And, instead of like in inference, you just discard them. You need to compute the other thing. The previous one, you can garbage collect it, or you can deallocate it or not deallocate it, but you kind of let it go. In the backward, you say, no, I need this. Stash it for me somewhere on the GPU, and eventually you get to it. But yeah, it's a lot of memory in the end.
right. I mean, so we can see it here a bit, and maybe I will like have more distinct sizes. If we have a function that just computes a matrix multiplication and we run this through the JIT, we see that we get, again, an output that has a grad fn. And if we look at the last traces, we see that, oh yeah, here it computes the matmul, and here it saves A and B for the backward. And you can look at the backward here too. If we look at the backward, and it's small enough to do this separately, of course, you always multiply the gradient with the appropriate other factor to get one factor, and then you need to transpose things. And you see this here, that you have a permute or transpose, which are equivalent. And then you have a matrix multiplication to compute one gradient, a matrix multiplication to compute the other, and then you return the two gradients. And this is what the backward does, very similar to what you would have for if you did an autograd function. Yeah, but inside, and we saw this a few weeks ago when we started out with the Triton bits, and I can see if I can. So there's a Triton example, and we had these transforms, and we had well, yeah, not in the first one, but in the oh, this is from the Liger, and we need to go backward until we find it.
It's a backward, yeah, and it also helps to name the notebooks appropriately, right? Usually,
Okay.
And that's what you need to do in the trace. You need to name your tensors in a way that you can understand.
Yeah, in July we didn't have Triton yet. And so this was September 13th here. Okay, and here we have the gradient transform. And remember that linear was essentially a matrix multiplication with an additional transpose. And so this is exactly what's here that we call the matmul. We replaced the matmul with our own custom one implemented in Triton. And this multiplication, this is the result that gets returned here by the function. And then we obtained the gradient of the output here with getGrad. And we computed the gradient input and weight from that. If you want to recap it, it was in September that we did this in video.
But you use weight and you use imp, right?
Yeah, and you reuse the inputs here. And this means that in order to compute these two lines, I mean, here they're presented in one function, but so this line will actually be computed as part of the forward, and then these two will be computed as part of the backward. If we split this for integrating with PyTorch. And so you have to store these two, input and weight, in order to compute the gradients later. And so
and weight, I mean, weight you have, unless you are distributed, you might need to kind of gather it. But imp is something that usually you could forget, right? Unless you need to compute the gradient, because weight is weight. Yeah. You have it there. Imp, not so much. And imp can be large, in transformers. And not only that, you need to save one for each operation. Yeah. So it's not just one input; it has many, 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 many inputs to whatever. And so how? Yeah. And so how do you deal with that within something like Thunder or whatever compiler
maybe
or not.
before like my brain hurts, we can like show it in the graph.
Yes.
So let
All
me
right.
stop sharing my screen.
Yeah. So
Oh, it doesn't.
here, you guys should see the thing, right? Uh, is that you see correctly? Great. All right. So what are we trying to do here? Essentially, we're saying we have, well, one convenient thing is that we're dealing with models that are basically straight line models. Yes, they are like skip connections, but one good thing is that a transformer, apart from the fact that it has something in the front, and then it's made up of many blocks. And then, I mean, it's like there's a residual stream here, right? But in any case, conceptually, each of these blocks is made up of things that are blocky as well. So you have an attention part, and then you have an MLP part, and then you have norms and stuff. But from a mile high, it's kind of that. And so you have a repetition of many things. And so basically what you do is I compute activations here, and then I compute activations here, I compute activations here, and then here. And basically, when you get to the output, and then you get to a loss, and then you call backward, basically you have to go back, ideally go back, but it's really, you put computation in front of you. So when you say backward, you need to recompute, because what you want to do eventually, if you have a weight matrix here, you want to also compute the grad, which is the partial derivative of the loss function with respect to those weights. And so you want to populate this tensor here with numbers, which means you need to put in front of you, you need to put more computations. And they're kind of playing backward whatever computation you did here. And so you basically need to say, okay, right, so let me remove this line that disturbs me a lot. Thank you very much. Okay, past me. And say, you saved all these things for backward. Now I need to grab this one, and use it here. And then you need to grab this one and use it here.
Yeah,
you need to grab this one.
That's because you have all the imps, like these are the imps,
exactly,
all the matrix multiplications, right? From the
exactly. And then, yes, as soon as you use those, then you can deallocate these, right? But not before. And then you go back in the other block, and you can see how much memory I need to use to even run my thing. Now, what you could do is say, okay, now maybe I can just, instead of, basically you have two things, right, in your scale. You have a scale where you have to, I'm studying mass and weight with my son now. And so I have the two things where you measure mass, and I was trying to explain him how, you actually measure mass and not weight if you have a scale like this. But anyway, you have memory, and then you have compute time. So you can trade, if you're to have your memory, you can say, okay, let me use a bit less memory. And this will go down. And usually computes go up in this case. It's not a universal law, but in this case it is. And you could say, okay, instead of saving all this stuff, maybe I can just not save all the intermediates here, but I can only save the intermediate at the in-between blocks, right? Or you can adopt different strategies and save one every, I don't know, whatever.
Yeah.
And usually you, go ahead.
Ideally, you would only save the memory that you can't afford or can't easily afford. So there is a thing where you can, well, you have several knobs to change memory usage, right? It can be
Yep.
sequence length, but then sequence length is usually given by your data or your model. You could also vary the batch size, but of course that's a very coarse thing, and like small batch sizes tend to be, if you have the memory, larger batch sizes are computationally more efficient, likely. Um, but then the third thing is, well, yeah, save less activations, right? And this is something where you could say, well, yeah, how many of these can I save, and how many of these should I avoid, right?
Exactly. And it's not that you need to save one at the beginning, one at the end, because what happens when you save fewer of them? What happens here is that instead of having all of them for your computation at your disposal, right? And here's the loss. And then you get the backward computations here. Instead of saying, oh, I need this tensor here, let me grab it from there. Now you don't have it anymore. Or maybe the first well, maybe not. Maybe you don't even have it. And so what you do is you go back, you replay the forward, and then you produce the intermediate activations, or you can do it step by step. But you compute all the activations that you need for that particular block until the next things you checkpointed. And then you have them here to use for the backward. Then you deallocate everything. So basically, you strike a trade-off between how many things you can save and how many things you need to replay.
Yeah.
And yeah, go ahead.
You said the C point, the C word here. So this is also called checkpointing, because you
Yep.
decide what to save for backward, and that is called the checkpointing. Of course, there's also this checkpointing in the sense of saving intermediate results
Yeah.
during the training, but this is now, if you want to clarify it, activation checkpointing, right? And so
Yeah.
you decide what to save between forward and backward.
Yeah. Another thing that you could do is move these out of the way, for example, right? And what you can do is like offloading.
Yeah.
Which is usually not
Here,
very convenient. Go ahead.
out of the way here means like off the GPU memory.
Oh, yeah, of course. So here are in GPU, you can offload to CPU. Now, the communication between CPU and GPU is not super fast. Maybe you can like prefetch, you can play smart here. One interesting thing that is happening is that modern GPUs start to have a CPU with unified memory on the device. And this is kind of shifting again the convenience, or potentially will shift the convenience of recomputing towards saving on the CPU and a unified memory, and then recalling them so that you don't use GPU memory, but it's fast enough if you do it early enough so that you don't have to recompute.
Right.
And this is one of the examples where, things will change as the hardware changes, right? So the fact that you can use unified memory on the device, and now you have more, could potentially make all these very smart activation checkpointing trick, blah, 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 completely be replaced with something that is a big no-no right now, which is communicating with the CPU. And so
Right.
that's why I think also the importance of having something, not just Thunder, but also like Thunder, where you can express and swap in transformations of your program, where you can say, okay, now let me try. Now you're on a new GPU, right? And you don't know if it's better for you to do activation checkpointing or do offloading on your not CPU, but kind of unified memory on the device. And that will be very dependent on the kind of data, how large is your activation, how long is your sequence, and whatever. So you need to play with it, variation of the things. And I think this is very important to be able to parameterize something like that check it, and then nail the kind of right trade-off here. Anyway, I'm going off a tangent here, but just to say that this is also what I think we call it. What do we call it in Thunder? It's rematerialization. Sorry. Yeah, getting old.
Basically, same thing. You forget about it, and it vanishes, and then it rematerializes.
Yeah, exactly.
There.
I didn't checkpoint it though.
Just by hard work.
Yeah, rematerialization. And in fact, you could also do things like, and we don't have that. We have a plan to do it, but we don't have it yet. And say, okay, now I have all my things here. Now, can I estimate how much free memory I will have at any given point in time so that I can decide on the fly, based on the available memory that I'm estimating, what to retain and what not, to strike a really quantitative trade-off between the two. And these are all things you can do once you can operationalize program transformations. Anyway, that's the thing. We go back to code now and we see how this plays out a little bit.
Yeah. You want to go back to code?
No. I mean, just see. Take a look. Maybe we could take a look at the rematerialization, or maybe just we can do it next time, and in the meantime we can just run the backward.
Let me grab share the screen again. Okay, so here we go. And here we are back in the notebook. And you want to see
yeah. So
you
rematerialization, or just run the Hugging Face, and then we can check the rematerialization the next time, because it's already it's been already 40 minutes. So I just noticed that. So
okay. So next time we'll see how to save the memory here. This time we used after the backward we have 11 gigabytes, but
it's not bad. Well, the model is pretty small, and then we have a big GPU.
Small model, small batch size, small sequence.
And we didn't compute a lot, because that usually when you need to compute the softmax and then the cross entropy, that is where.
Well, we do have that, but we're actually, I think one of the things is true. that we are past the backward. So if we look at this, you would expect that as you compute this line, right, you would expect the memory use to go up.
Yeah.
No. And then for the backward, we would expect the loss to go down again.
Because we free things up. Right.
A bit more next time.
Yeah. Okay, that's good. Very nice. All right. So if you want to know more about this and you really want to be committed to understanding rematerialization, there's a rematerialization transform in Thunder that you can take a look at. It's not easy to follow because the logic is, complicated because it is. But it's there. It's there to see. It's just basically one or two functions, and it's all in there. All right. So thanks for the walkthrough, Thomas.
And, you did all the explaining with the graphs. It's awesome that we don't just do coding, but also have the scribbling.
Yeah, I forgot to draw one of my little characters this time, but next time.
Yeah, for the little characters, tune in next week.
Exactly. Thank you, Thomas. Have a great weekend.
You too, Luca.